I don't have PowerPoint for you. It shouldn't take too long. We're going to talk about sketching rational functions. Okay. So I gave you a handout on the steps. Yes, and you have those steps in front of you. And but first of all, I want to talk about in general. You can have what they call a parent function. Parent function. So for like a parabola, the parent function is y equals x squared. For a hyperbola, the parent function is 1 over root of x, or excuse me, 1 over x. And what does that parent function look like? Because it's good to have some idea what these things look like, so you don't have to every single time find the asymptotes, find the intercepts. You can just have an idea of what it does. What does this look like again, Isaac? That's right. It looks like one of these hyperbola going that way, and a hyperbola going that way. Now, the other thing, some of your graphing calculators, you got to be careful because some of your graphing calculators will end up connecting. They'll put the asymptote in there for you, and that's a confusion because they're not continuous. Sometimes they put in, I don't know, the calculators, they can distinguish between an asymptote and a discontinuous function or something, and they graph this part. So don't be confused when you see something like this. It doesn't mean that this is part of the function. It means that it's an asymptote. Okay. So did any of you run into that on your calculator? Okay, that's good. I think that might be on the older ones anyway. So if this is y equals 1 over x, what do you think y equals 1 over x minus 3 would look like? What does that do to my graph? What does x minus 3 do to a parabola? Shifts it 3 units to the right. So with this thing, it would do the exact same thing. It would shift that hyperbola, this hyperbola, over, and you can see that it's going to have an asymptote where? Where's the vertical asymptote? At x equals 3. So it's going to look exactly like this, but instead of the y-axis being the asymptote, x equals 3 is the asymptote. So that looks like that. What if I did y equals 1 over x plus 2 minus 3? What's that minus 3 at the end going to do to my graph? Shift it down 3, okay? What's this 2 going to do to my graph? Left 2, okay? So that's kind of the same idea as with your other function. So I know that I have an asymptote at negative 2, right? And I also know that I have that it's going to be shifted down 3. So where this has an asymptote at y equals 0, as does this, now I'm going to have an asymptote at y equals 3. I should use my straight line tool. Y equals 3, okay? And y equals negative 3, right? Sorry. And this is x equals negative 2. And then it would look, so you could just kind of sketch the graph. You could find the y-intercepts pretty easily, and the x-intercepts for that matter. This one's going to look something like that. Okay? Questions about that? How you can shift hyperbolas and stuff? So, and if I want to find this point where it actually crosses the x-axis or y-axis, I would just plug in 0. 1 over 1/2 minus 3, what's that? Negative 2.5. So that would be the point 0, comma, negative 2 and 1/2, I think, right? Negative 2.5. And I can find this by setting the top equal to 0. But you say, wait a minute, the top is never 0. Did you say that? But the top can be, because really to make the top equal to 0, you have to find a common denominator. So I would have to multiply this. I'm not going to make you do this, but I would multiply this by 3x. I would multiply this by x plus 2 over x plus 2. See, and then the top becomes 1 minus 3x plus 1 minus 3x minus 6, right? Over x plus 2, which gives me negative 3x minus 5 over x plus 2, which tells you that when this is 0, when x equals negative 5/3. So this point right here would be negative 5/3, comma, negative 5/3. Let's try that again. Let's try, negative 5/3. What happens? Where'd my thing go? There it is. So this point here would not be a scribble. It would be, oops, I'm trying to get the right tool here. That point right there would be negative 5/3, comma 0. Negative 5/3, 5/3. Okay. So that's just some basics about parent functions. Okay. Now let's sketch a more complicated one using all those rules that I gave you, and we'll talk a little bit about Celan asymptotes and stuff like that. So you ready? Let's not use that paper. Let's sketch y equals 2x minus 1 over x. And if you just kind of go through this process of finding all the things on that sheet that I gave you, you should be pretty good. Okay? So first, what's the first thing say? What does it say on that sheet? Yellow sheet. Simplify by factoring. Can I simplify this anymore? Go like this. No, you cannot simplify it anymore. Find the y-intercept by plugging in 0 for x. So when I plug in 0 for x, what do I get out for y? 0 comma what? Uh-oh. No, I get negative 1 over 0. What's negative 1 over 0? It's this thing, infinity, right? So what do I have at x equals 0? I have an asymptote. X equals 0, I have a vert asymptote. So we kind of find that asymptote kind of accidentally, right? So I have a vertical asymptote right here, so I know this is a vertical asymptote. And that agrees because that's where the denominator is undefined, right? And so we can't really, so there is no y-intercept because the y-axis is an asymptote. X-intercept. What's the x-intercept in this case? Set the top equal to 0. So 2x minus 1 equals 0. Simplify, I get x equals 1/2, right? Huh? So that's the x-intercept. So if this is 1, let's call this 1/2. So I know that this graph crosses here. Right? I did that. What did it say to do next? Find the holes by finding common factors of the numerator. Are there any holes in this graph? Does anything cancel out from the top and bottom? No holes. No holes. Okay? No holes, so we could skip that step. Find the vertical asymptotes. We did that. Find the horizontal asymptotes using those rules I gave you. What's the horizontal asymptote? Y equals 2. Does everyone see why y equals 2 is a horizontal asymptote? Because the degree of this is the same as the degree of this, and the ratio of the coefficients is 2 to 1. That's how we find that there's a horizontal asymptote. Whoops, I don't want that. There's a horizontal asymptote at y equals 2. Okay, so I'm going to make a dotted line. I'm going to go like this. And let's say that this is, we're going to sketch it in. Y equals 2 is my horizontal asymptote. I know it goes through this point. I also know that this is a vertical asymptote, right? What else does it say? Give the degree, use the long division. Graph as much as you know up to this point, including the whole dotted lines for asymptotes. Pick some points between the vertical asymptotes, x-intercept. Complete the graph by filling in the check to see if you're right on the graphing calculator. Note that this option will not be available on a test, okay? So what do you think this curve looks like? Class, if the y-axis is an asymptote, and this is an asymptote too, and it goes through this point. Can you sketch it in? Where does it go? It's right? Yep, it's going to go like this, I believe. Whoops. Doesn't hit the asymptote. And then probably it's going to go, does that make sense? Is that right? And then it's probably going to go like this. That doesn't make sense. It should be.
How did it go?
Did I mess up? X equals 2x minus 1. I think that's what it should look like. Let's check with the graphing utility. Okay? Does it look like that? I was right. That's what it looks like. Do you want me to check with the graphing utility? Do you believe me? Let's try.
So, Mr. Leader, if we hadn't found the 0, is there another way to know that it was flipped in half?
Yeah,
Well,
X does most.
What?
That's right.
That's right.
Does most.
Is there another way? How do I know it's flipped like that? I know it's flipped like that because I know this is an asymptote, right? I know that this is an asymptote, and I know that it has to go through that point,
I'm
right?
just saying, is there another way to figure it out?
If it's flipped,
Yeah.
you have to kind of plug in some points and figure it out. Now, some cases you're going to get parabolas or hyperbolas that kind of are symmetric. You know, they're kind of both positive, and usually you get those when you have like squares up here and stuff like that, because it's kind of going to be even and things. So if you have like y equals 1 over x squared, that's going to look something like this. You know? All right? Okay, but usually you have 1 on one side. They have symmetry, you know, kind of rotational symmetry. All right, so moving on. Let's do another one, because that one wasn't very exciting. Let's do, let's look at slant asymptotes. Okay, so Reed already knows about slant asymptotes. Slant, or sometimes they call them oblique asymptotes. And what a slant or oblique asymptote is, it's a line that the function approaches that is on a slant, right? So if this is an asymptote, I might be approached as x gets infinitely large. I might be doing something like approaching this line, okay, over here. That's not a very good curve. We're approaching this line over here. So that's, or it might be, oh, it wouldn't be over here because then it wouldn't be a function. So that's, when you have slant asymptotes, you'll get a graph that looks like something that looks like that. You know you have a slant asymptote if the degree of top is 1 bigger, okay? Bigger than degree of bottom. 1 bigger than degree of bottom. Okay, degree of the numerator is 1. Because, well, we'll do an example. But if it's more than 1 degree, then it's going to approach some curve or something like that, like a cubic or a quadratic, and we're not going to worry about that. And I think you'll worry about that in higher level math classes, but not in this class. So let's do one where you have a oblique asymptote. So, and we're just graph y equals x squared minus x over x plus 1. The way you find a slant asymptote is you use long division, okay? So you just take this and you divide it into this. So slant asymptote, you go x plus 1 into x squared minus x. And the nice thing about this, usually, yes, sir.
Can I use the restroom?
Yes, sir. Okay.
Thanks.
Yes, sir.
Did you do synthetic division for that?
Could you do synthetic division?
Because it's just an x plus.
Oh yeah, I guess you could. You could on that one because it's just an x plus 1. But if you have the case where you have x cubed something over x to the 4th, so kind of, you know, I think it's easier if you just remember to use line. And you're never going to have to go more than 2 steps because the slant asymptote is always going to be the equation of a line. So you're never going to get like a quadratic as your quotient, okay? So you're always going to get the equation of a line as a quotient, and that's your slant asymptote. It's just a quotient part, not the remainder. So what do I need to multiply x by to get x squared? X, right? So, and I'm going to put that x up here, and this times this gives you x squared plus x, and then I subtract, okay? And this goes away. Minus x minus another x gives you minus how many x? Minus 2x. Minus 2x, right? What do I need to multiply x by to make it into minus 2x? Negative 2. That's your slant asymptote. Y equals x minus 2. You don't have to worry about the remainder. Once you're there, once you're at this point, since it's always going to be the equation of a line, there's going to be a remainder, but you don't have to worry about it because it's going to approach this line. Because if I went further, I just get a remainder, and the remainder is not going to help you. So when I graph this one, where's my workspace keep going? When I graph this one, it's weird how that kind of disappears and then it comes back. Whoa. I'm going to have a line at y equals x minus 2, which looks like, let's put arrows on the end. Arrows. Whoa, this is doing some weird stuff, man. There, here, okay? I don't know what this is going to look. Here's a line. Y equals x. Is that y equals x minus 2? Close enough, okay? I'm not done graphing yet, okay? So we have an asymptote. Here's my asymptote. Let's find the zeros. What are we supposed to do first on this? We got ahead of ourselves, okay? On the list it says simplify the numerator and denominator. Can I simplify the numerator? Can I factor something out of x squared minus x? What? X. So I'm going to write y equals x times x minus 1. And on the bottom I have x plus 1. Okay? Okay, so I can't, can I cross anything out? Can't cross anything out. So there's no holes, okay, because I have an x minus 1 and x plus 1. I can't cancel those out. But I do have 0. So the next step did that by factoring out. Find the y-intercept by plugging in 0 for x. What's the y-intercept? Plug in 0 in here. We're here. What do I get out? 0 minus 0 over 1. What do I get out? 0. So the y-intercept is 0, 0, which means it goes through this point right there. See that? X-intercept. Is that the next thing? Find any holes. We don't have any holes. Find the x-intercept by setting the numerator equal to 0. So I'm going to set the top equal to 0. So x times x minus 1 equals 0. What's going to make that 0? Two things. X equals 0 and x equals 1. Well, I already have this x-intercept. The x-intercept and the y-intercept are the same, right? Because that's 0, 0. But then I have another one at 1, 0. I'm not sure which side of the line this is on. What's this line? Y equals x minus 2. So it's on the left side, right? It's here. Okay, so here is the point 1, comma 0 is on the graph. Okay. Do I have a vertical asymptote? Oh, I'm not done yet. Am I? The highest degree, where are we? Find the holes, find the vertical asymptotes by finding the zeros of the denominator. Do I have a vertical asymptote? Where's the denominator equal 0? Vert. So y equals negative 1 is a vertical asymptote. And so at -1, I have another line that's going to come down like this. Okay? And that's an asymptote at y equals -1. So I have a vertical asymptote. I have a horizontal asymptote too. No, I don't have it. You can't have a slant asymptote and a horizontal asymptote. You either have one or the other. Okay? So I don't have any horizontal asymptotes. We found the slant asymptote. Graph as much as you know up to this point, including the holes, dotted lines for asymptotes. How do you think this curve looks? If this is an asymptote, it goes through these 2 points. I am going to guess, I'm going to use a nice green, what color should I use? This nice color? It's got to go through these 2 points. These two things have to be asymptotes. So what do you think it looks like? It's going to go down, I'm pretty sure it's going to go down from here, hit that point, go through here, and then approach this asymptote like that. Okay? And it's going to have some symmetry to it, so down here, it's going to do a similar thing. Okay? You know why I know it's not doing this over here? Oh wait, I don't know it's not. Yeah, I do. Because these 2 points, because I know it's got to go through those 2 points. Okay, so if you graph that on a calculator, you would get something that looks like that. You believe me? Okay, I'm not going to do it. Do you want me to do it? Let's do it. It's fun. Y equals, what are we graphing? X squared minus x over x plus 1. So the top you have to put in parentheses, x squared minus x, close parentheses, divided by parentheses x plus 1, x plus 1, close parentheses, graph. Come on, baby. There you go. Look, just like I said, huh? And the asymptotes, you can't see them, but they're there. Okay? I think there's a way to, does that look like that? Pretty good, huh? For just using math, you know, rather than doing that. So it looks pretty similar. What else do I have for you? I'm gonna let you work, okay? You do have some that sometimes with you remember how to find the holes. You guys remember how to find the holes? Okay. Wasn't there a movie about that or something? Is that what they find, the holes? What is it about? Is it, huh?
I think treasure.
Oh, treasures. It's not about asymptotes and things.
No. Yellow piece of paper.
A yellow piece of paper. Oh yeah. Oh, you didn't get one.
No.
Okay. So I'll just shut up here, and sometimes, let me just say one thing. Sometimes, like in the case of something like this, x squared minus 9 over, you can have like 2 asymptotes. You could have 2 asymptotes and weird stuff going on. Like, which one was it? X squared, x squared, y equals x squared. I'm not going to go through the whole thing. Minus x minus 2 over x minus 1. Oh no, that's not the one. Okay. Sorry, I messed up. In the case of x over x squared minus x minus 2, x squared minus x minus 2, you end up getting something with 2 asymptotes, one at plus 1 and one at negative 2. And what you end up getting is something that looks kind of like, and then you have an asymptote at y equals 0. You end up getting something that looks like this here and this here. And in the middle, you get something that looks like this. Okay? And so this graph will give you this. And you can find those asymptotes. You can find the intercepts. You could find all the asymptotes, but then you might have to plug in some points to kind of get a picture of what the graph's doing in between. So with something like that, it'd be more difficult. Okay? All right, you want to know what your homework is? You don't? Page, not you, Paige. Page 157. 157, 1 through 6, 14, 16, 17, not too many, 22, that says 27, 22, 27, 32, 40, 51, 70, 85, and 89. Okay? So that's all you're doing in this stuff is just